the European social class for atom. CERN's research reveals specifics of another molecule, the smasher. Today, on different occasions, it is more huge and also twice as important. It has featured 3 new items that could be useful in sorting out how our universe was envisioned and what its future appears to be. Experts at CERN have recently exposed details that altered our behavior, interpreting the universe upside down. The outer layer of their colossal tests lies an enormous swath of particles and control, so curious that they might be straight, far away from conceivable parts to substitute viewpoints. Particles that challenge the veritable clarification of the genuine. What stupefying, advantaged pieces of information are private inside these tests? Could we, at some point, leap into the CERN universe and loosen up the pieces of data that could re-evaluate our universe? The segment to New Views characteristics, a wormhole, could theoretically appear all of a sudden above. The wonderful thing would be clarification. Assessments driven at CERN, home of the Titanic Hadron Collider, LHC, the world's greatest and most powerful particle smasher located near Geneva, riding the line between Switzerland and France, contain exclusive information about this remarkable affiliation that the rest of the world lacks. Some relationships in insider facts could alter our perception of the material. To tell you the truth, the European Organization for Nuclear Research works this huge, unimaginable instrument. It expands over 27 kilometers and sits underground. The inspiration behind the Large Hadron Collider is to give physicists the ability to evaluate the opinions of diverse theories regarding atomic material science. This solidifies the high-profile investigation of the typical model of particle science, which helps us in sorting out the fundamental structure of the universe's fundamental blocks. The Large Hadron Collider works by accelerating protons to close to the speed of light before colliding with one another. These effects result in an abundance of new bits, studded particles, offering information into the rules of nature. It was through such starters that a significant portion of the Higgs boson, also known as the God particle, was found in 2012. This straightforwardness demonstrated the veracity of how particles acquire mass, which was an enormous moment in the study of atomic material. The tests driven at the Large Hadron Collider are essential for figuring out attributes that occur under extreme conditions, essential yet unclear, from those long after the Big Bang. The data amassed can fill us in on more about how the universe was created, grown, and about the fundamental constituents of matter. This makes the Large Hadron Collider a player in uncovering new pieces of reality, including dark matter and the central forces of nature. Such high-level experimentation at CERN doesn't come without reservations. Some speculate about high-energy tests producing black holes or captivating matter that, at any rate, could introduce risks to Earth. CERN ensures that all safety measures are met, and arranged experts closely monitor these assessments. Studies on hypothetical models affirm that any risky situations are extremely unlikely. Through its consistent investigation and opportunities, CERN aids us in better organizing the universe and demonstrates the remarkable limitation of human development and cooperation. The LHC's data-seeking mission is humanity's continuous, strong event. The bewildering Hadron Collider is not simply an impossible development element, it is a marvel of contemporary science and engineering. Built under the Swiss-French border, the giant collider goes through a passage 27 kilometers in width and is generally as much as 175 meters deep underground, making it the best particle collider in the world and one of the main instruments in the field of material science. The particle development of the Large Hadron Collider is planned to conduct large-scale surveys. The head ring of the collider, housed in a passage with a breadth of 3.8 meters, contains 2 identical connecting pipes. Each line organizes protons in the opposite direction, rapidly driving them with a progression of superconducting magnets. These magnets are central for maintaining the proton's course at speeds close to that of light. Surrounding the beam pipes are layers of cooling structures that keep the temperature colder than space, designed to preserve the superconductivity of magnets at their working temperature. The size of the gigantic Hadron Collider is also underscored by its utilization of remarkable magnets, including 1,232 dipole magnets used to bend the beams and quadrupole magnets to concentrate them. The best and most powerful superconducting magnets utilized are 15 m long and weigh 35 tons each, showing the gigantic scope and mechanical ambitions behind the collider. The main objective of the Large Hadron Collider is to investigate the universe's composition by seeing the smallest bits of matter. By propelling particles to nearly the speed of light and colliding them, the massive Hadron Collider allows physicists to focus on the particles created in this process. These effects aid in testing and expanding our comprehension of the standard model of atom science, the most effective description of the subatomic world. One of the key targets behind the Large Hadron Collider's tests is to uncover the insider realities of the Higgs boson. Its discovery at CERN in 2012 confirmed theories about how particles obtain mass. Additionally, the Large Hadron Collider studies fundamental forces and particles, attempting to answer basic inquiries, like the presence of dark matter and the nature of the universe shortly after the Big Bang. The Large Hadron Collider aims to confirm the presence of new particles that speculative material science predicts but has not yet observed. These evaluations are key for potentially discovering new material science beyond the standard model, such as supersymmetry and perspectives beyond the traditional three-dimensional view. The purpose of the amazing Hadron Collider isn't just to understand the universe's arrangement but also to support worldwide collaboration. With experts from more than 100 nations participating, the Large Hadron Collider is an endorsement of cooperation in the quest for knowledge. Its design and scale empower it to tackle the most severe questions in material science beyond simple scholarly curiosity, aiming to revolutionize how we unravel the universe and support global scientific cooperation. Through this vast and complex device, humanity continues to challenge the boundaries of what is known and experienced in the quantum domain. But how does the Large Hadron Collider really perform? At the heart of the evaluations, the Titanic Hadron Collider serves as a force multiplier, incorporating quantum space and allowing scientists to observe and analyze the most important particles that constitute the universe. The process of particle speed acceleration and the Large Hadron Collider's impact is a fundamental method for evaluating the foundations of material science. Within the collider, two high-energy particle beams travel at nearly the speed of light before colliding. These beams travel inside tubes kept at ultra-high vacuum, mimicking the conditions of superconductivity in space. Electromagnets, cooled to temperatures colder than space, help steer and gather the beams at predetermined points of impact. The discovery of the Higgs boson at CERN in 2012 was a groundbreaking moment in particle physics. It provided confirmation of the Higgs field, a crucial component of the standard model, which explains how particles acquire mass. Without the Higgs boson, fundamental particles would remain massless, making the formation of atoms, and, by extension, the universe as we know it, impossible. However, the Large Hadron Collider, LHC, is not solely focused on the Higgs boson. Scientists at CERN continue to push the boundaries of physics by investigating other fundamental forces and particles. One of the most intriguing aspects of modern physics is the search for dark matter, a mysterious form of matter that is believed to make up about 27% of the universe. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it invisible to traditional detection methods. By recreating high-energy collisions similar to those that occurred moments after the Big Bang, the LHC allows physicists to search for theoretical particles, such as WIMPs, weakly interacting massive particles, and actions, which could help explain the nature of dark matter. If such particles are detected, they could revolutionize our understanding of the cosmos, providing insights into the unseen structure of the universe. Beyond dark matter, another goal of the LHC is to explore the concept of supersymmetry, a theoretical extension of the standard model. Supersymmetry proposes that every fundamental particle has a heavier counterpart, or superpartner. If proven, this theory could help unify the forces of nature and provide a deeper understanding of gravity, potentially bridging the gap between quantum mechanics and general relativity. The experiments conducted at CERN also have practical applications beyond theoretical physics. The technologies developed for particle accelerators have contributed to advancements in medicine, computing, and engineering. For example, CERN's research has played a role in the development of medical imaging techniques, such as PET scans, and even the creation of the World Wide Web, which was originally designed to facilitate data sharing among scientists. Despite its many achievements, the LHC has also sparked controversy and speculation. Some conspiracy theories suggest that the collider could create microscopic black holes or open wormholes to other dimensions. However, physicists have repeatedly assured the public that these scenarios are highly unlikely and that all experiments at CERN adhere to strict safety protocols. According to theoretical models, any black holes produced would be minuscule and would evaporate almost instantly due to Hawking radiation, posing no threat to Earth. Looking ahead, CERN is planning upgrades to the LHC, including the High Luminosity Large Hadron Collider, HLLHC, which is expected to be operational in the 2030s. This upgrade will increase the collider's luminosity, allowing scientists to collect more data and observe rare particle interactions with greater precision. As humanity continues to push the boundaries of knowledge, the Large Hadron Collider remains a symbol of scientific progress and international collaboration. With contributions from thousands of researchers across more than 100 countries, CERN exemplifies the power of collective human effort in the pursuit of understanding the fundamental nature of reality. The mysteries of the universe remain vast and largely unexplored, but with each experiment at the LHC, we take another step toward unlocking the secrets of existence. Whether through the discovery of new particles, insights into dark matter, or deeper understanding of the fabric of spacetime, CERN's work continues to shape the future of science and technology. In 2012, this particle was discovered in boson. Referred to as the God particle, it is significant because it demonstrates the Higgs field, which is responsible for giving fundamental particles mass. The Higgs boson was anticipated by the Standard Model, and its discovery was an extraordinary achievement, affirming long-held theoretical assumptions. Beyond the Higgs boson, the Large Hadron Collider has also been instrumental in the discovery of a variety of other particles. For example, the collider has provided evidence for the existence of confined quarks and confirmed the presence of tetraquarks, particles consisting of between 4 and 5 quarks. Each of these discoveries adds to our understanding of hadronic matter, which is matter made of quarks bound together by the strong force that holds atomic nuclei intact. These discoveries demonstrate the strength of the Standard Model and open new avenues for investigation into particle science, offering insights into the behavior of matter under extreme conditions, such as those shortly after the Big Bang. Speculative dangers, like strangelets or miniature black holes, have been subjects of public interest and ongoing examination. Strangelets are a hypothetical type of matter that is more stable than ordinary matter. The theory proposes that strangelets could convert anything they come into contact with into strange matter. The fear surrounding this theory is that if strangelets were created during particle collisions at the LHC, they could potentially convert Earth's matter into strange matter. However, extensive research conducted by CERN and the global academic community has addressed these concerns. Research has demonstrated that even though strangelets, if they exist, might be produced at the LHC, they would likely be highly unstable and decay too quickly to influence the amount of matter on Earth. Furthermore, high-energy galactic rays and space debris consistently strike Earth with much higher levels of energy than those created by the Large Hadron Collider, yet no strangelets have been observed forming. This natural evaluation suggests that strangelets are not a significant risk. The concern that the Large Hadron Collider may produce tiny black holes comes from speculation about extra dimensions in physics. Some theoretical models suggest that high-energy impacts inside the LHC could create tiny black holes that would immediately disappear due to Hawking radiation, a type of radiation predicted by physicist Stephen Hawking. However, scientists agree that even if black holes were ever created at the LHC, they would pose no harm to Earth. Ongoing experiments at CERN and the LHC have greatly improved our understanding of physics, while also raising intriguing and significant questions about the nature of reality itself. The tests conducted at the LHC are shaping the future of physics, not only by confirming theories but also by potentially uncovering entirely new scientific domains. The discovery of previously unknown particles or forces could redefine our understanding of space, time, and the fundamental structure of the universe. For example, the search for dark matter and dark energy, two of the biggest mysteries in modern physics, is a major focus of ongoing research at CERN. While we cannot directly observe dark matter, its gravitational effects on visible matter provide clues to its existence. The LHC could help determine the constituents of dark matter by causing them to collide or by uncovering how their elusive properties interact with other subatomic particles. Similarly, dark energy, thought to be responsible for the universe's accelerated expansion, is another mystery researchers hope to better understand through experiments at CERN. Another area of interest at CERN is research into supersymmetry, a theoretical framework that suggests relationships between fundamental forces and particles. Supersymmetry proposes that every known particle has a corresponding superpartner. Finding evidence for supersymmetry would be groundbreaking, as it could help explain some of the universe's biggest mysteries, such as the nature of dark matter and why particles have the masses they do. Theoretical ideas like string theory, which suggests that fundamental particles are actually vibrations of tiny strings, are also being indirectly tested at CERN. While string theory remains speculative and largely untested, any experimental evidence supporting it would revolutionize our understanding of the laws of nature. In addition to these advanced scientific inquiries, CERN's work has practical applications that benefit humanity. Technological advancements developed at CERN, especially in computing and particle detection, have contributed to various industries. For example, the World Wide Web itself was conceived by CERN scientist Tim Berners-Lee in the late 1980s to facilitate the sharing of research among physicists. Advancements in imaging and medical technology emerging from CERN's research continue to have far-reaching impacts, demonstrating how fundamental research can lead to unexpected and valuable innovations. Collaboration at CERN is also a vital component of its success. Scientists from over 100 nations work together at CERN, sharing knowledge, ideas, and expertise. This cooperation fosters a climate of creativity and innovation, where breakthroughs are often achieved through the combined efforts of the global scientific community. The LHC itself is a symbol of this collaboration, bringing together thousands of researchers, engineers, and technicians to work on one of the most complex scientific instruments ever built. However, as with any groundbreaking research, CERN's work raises ethical and philosophical questions. What do the discoveries made at CERN mean for our understanding of the universe and our place within it? How might society interpret the outcomes of these experiments, particularly when they challenge long-held beliefs about the nature of reality? These profound questions drive ongoing debates not only within the scientific community but also among philosophers, ethicists, and the general public. As CERN pushes the boundaries of human knowledge, it also challenges us to reconsider fundamental aspects of existence, from the structure of reality to the origins and fate of the universe. One of the most intriguing aspects of CERN's research is its potential to uncover new forces of nature. While the standard model of particle physics has been remarkably successful in explaining fundamental interactions, it remains incomplete. For instance, it does not account for gravity in the same way it does the other fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force. The search for a theory of everything, one that unifies all forces, including gravity, remains one of the ultimate goals of physics. Some theorists believe that evidence of extra dimensions, undiscovered particles, or deviations from standard model predictions could emerge from LHC experiments, offering crucial clues toward this grand unification. Moreover, CERN's research has implications beyond theoretical physics. The technology developed for particle accelerators has already found applications in fields such as medicine, energy, and computing. For example, advanced imaging techniques used in medical diagnostics, such as PET scans, have their origins in particle physics. Proton therapy, a cutting-edge treatment for cancer, relies on principles developed through research at facilities like CERN. The ongoing refinement of these technologies could lead to even more effective medical treatments in the future. Another area where CERN's work could have a transformative impact is quantum computing. The immense amounts of data generated by the LHC require advanced computational techniques, including machine learning and artificial intelligence. As a result, CERN has been at the forefront of innovations in data processing and high-performance computing. These advancements could eventually contribute to the development of quantum computers, which have the potential to revolutionize fields ranging from cryptography to materials science. The international nature of CERN also plays a crucial role in fostering peaceful cooperation between nations. At a time when global conflicts and divisions persist, CERN stands as a testament to the power of scientific collaboration. The shared pursuit of knowledge transcends political and cultural barriers, uniting researchers from diverse backgrounds in a common goal. This spirit of international cooperation is one of CERN's most significant achievements, demonstrating how science can serve as a bridge between nations. Looking ahead, the future of particle physics is filled with exciting possibilities. CERN is already planning upgrades to the LHC, including the High Luminosity Large Hadron Collider, HLLHC, which will increase the collider's luminosity and allow for more precise measurements of rare particle interactions. Beyond the LHC, discussions are underway for even more powerful accelerators, such as the proposed Future Circular Collider, FCC, which could reach energy levels far beyond those currently achievable. These next-generation facilities could unlock even deeper insights into the nature of the universe. At its core, CERN's mission is not just about understanding particles but about understanding existence itself. Every experiment conducted at the LHC, every theoretical breakthrough, and every new discovery brings us closer to answering some of the most fundamental questions ever asked. What is the universe made of? How did it come to be? What are the ultimate laws governing nature? While we may not have all the answers yet, one thing is certain. CERN's research is reshaping our understanding of the cosmos and will continue to do so for generations to come. The discoveries made at CERN today may lay the foundation for the scientific revolutions of tomorrow, opening new doors to knowledge and transforming our perception of reality itself.